Oh, okay, great.
Shall we?
Okay, hello everyone. Welcome to EGRAPHS' workshop 2026. Thanks for coming. I think we should just go ahead and get started with the program. Speakers, quick note, your time slot is your time slot. You may use as much of that as you would like for questions, but I will kick you off sharply because we have a full program. So without further ado, Cheng, please take it away.
Hi, so I'm Cheng Zhang from Worcester Polytechnic Institute, and today I'm going to talk about our collaborative work with Sam Coward, Philip Zucker, which is in the audience, and Alexandra Silva on incorporating fixed point equation into eGraph. So I first have a little bit of disclaimer. This work is very much a work in progress. I found a counterexample last Friday night, and I cried myself to sleep. And everything you see is frantically edited today at 4 a.m. And I need another sip of coffee. Things on the slide are probably incorrect and inelegant, but I hope I can convey an intuition of why this should work, and yell at me if you see anything obviously stupid. We might acknowledge you in our paper if you do. So I'm going to make everyone happy to say eGraphs are great. And now I'm going to make everyone sad by adding a quantifier to say they are great for algebraic theories. And for example, this is a very typical example used in EG. And you will see a lot of eGraph operations works very well for these because they correspond to algebraic theories where axioms are user-provided equalities, substitution are defined by E-matching, congruence are by rebuilding, and equivalence closure are done by E-classes. So everything is great, everything is nice, but then we remember we are computer scientists, so we care about programs. For example, we want to sometimes reason about control flow. In here, we have an if statement where one branch executes a function, the other branch recurs, and a if statement where the first branch executes the function and the second branch recurs. And we sometimes also want to reason about data flows. In here, it's an SSA form, and we can turn this SSA form into streams. And these streams are also recursively defined. For example, if J starts with the initial assignment of 1, and if the first element of k is less than 10, i.e. the while loop, and then if the first element of j is less than 2, we execute the first condition, otherwise we execute the second condition. So these are programs that are not very native within eGraph. And what is missing within eGraph is that programs are really fixed point equations. Right? Recursive program can be specified as fixed point equations, and they actually admit more equalities that are beyond the standard algebraic equalities. Specifically, fixed point equations have solutions. And if the solution coincide, we should be able to merge these E-class as well, and that corresponds to bisimulation. That is something I want to convince you for this talk. So let's look at a concrete example of how this solution coincidence work. This is the control flow example we have seen before. And we know that if B then S else R is equal to if not B then R else S, right? We are basically switching the branch of the if statement, and they should be the same. And we can rewrite via this rewrite rules, and we get a new fixed point equation. And we notice in this fixed point equations, P and Q are actually defined in exactly the same way. Therefore, we can conclude P equals to Q. Right? So this is basically the intuition behind this. We have fixed point eGraph, where the equality are split into two. One of them is recursive definitions, where you define your program, you define your variable, you define your data flow. And then we have rewrite on these recursive definitions, right? And these rewrites allows us to manipulate the fixed point equation to try to exhibit equalities. And the operations on these are inserting definitions, saturate by rewrites, and also saturate by bisimulation. And clearly, saturate by bisimulation is the most interesting part, and I will try to demonstrate how this operation works. So for here, we have the recursive definition. First, we insert the first recursive definition into the eGraph. And one of the things you notice is that in the first recursive definition, it says P equals to this huge if-then-else statement. And yet, the if-then-else statement and P are not within the same E-class. This is the mistake I made on Friday night and cost me a lot of pain. So we want to keep recursive definition opaque in the eGraph. And similarly, we can insert the recursive definition of Q. And because we have this rewrite rules, we can saturate via this rewrite rule. Specifically, in here, we notice that there's a pattern that matches the rewrite rule. Therefore, we are going to insert another node to the back to the left side of the right side of the rewrite. Okay. And this is a very important point, is that variable unfolding are opaque with respect to the eGraph, in that sense that variable unfolding are not handled by the eGraph, only the rewrite are. So how do we handle variable unfolding? This is via transition systems. So given an eGraph, we can turn it into a transition system. In order to do this, I first marked all my E-classes. You can think of them as like E-class ID on top of it. And there are two ways to generate transitions. First one is stripping function symbols. So for example, if we start with the definition of P, which is the P-def E-class, we can strip the function symbol if then else, and we will get the E-class XF and P, right? That is simple enough. You are basically reversing the arrow on the eGraph. And another way to generate transition systems is by unfolding definitions. In here, for example, we notice that P is a variable E-class in the sense that it contains a variable P in there. We can unfold it into its definition, which is the P-def E-class. However, we mark this with a little colon equal sign to indicate that this is lifted by unfolding a definition. Okay. And in the same way, we can have the E-class for the definition of Q. We can lift it to have these kind of variable unfolding. And then we have the E-class for another way to define the definition of Q, which involves negation. And finally, we can also unfold the variable E-class Q there by linking it back into the definition of Q. In particular, we notice that these two looks very similar, right? If we replace P-def with Q-def, which are just a E-class, these two looks exactly the same. And this is where the bisimulation comes in. When we give these two the E-class that looks similar, we can construct a bisimulation on top of it. And if you read really hard into this definition, into the definition of bisimulation, it kind of extracts a fixed point equation. So this fixed point equation is if x equals to 0, then execute function, else recurse. This is exactly the fixed point equation we exhibit in the beginning to demonstrate that P and Q are supposed to be the same. And bisimulation exactly is doing that. So intuitively, bisimulation are extracting a fixed point equation that unifies the solution of two E-classes. And therefore, we can saturate by bisimulation because the equality is valid. And finally, we get this eGraph where the definition of P and Q are saturated. And because when we merge definition E-class, it's also good to merge their variable as well. So P and Q are also saturated together. And therefore, fixed point equation and EGRAPH lives happily ever after. Right? This turns out to be incredibly hard. So first challenge, it's sound rewrite versus sound equalities. So here it's a recursive definition where x is equals to 1 cons of x and y equals to 1 cons of tail of y. If you write this in Haskell, it will actually give you x. It's an infinite stream of ones. And y will have 1 as the first element. And if you try to get the second element or the third element and so on, you will run into infinite loops. Right? So in here, we can see that the semantics of x and it doesn't equal to the semantics of y. But let's consider the rewrite rule. X equals to tail of x. This indeed is a sound equality because if we take the tail of x, it's also an infinite stream of 1, and that is indeed equal to the semantics of x. However, it's not a sound rewrite because we can rewrite the fixed point equation into the fixed point equation on the bottom, and by bisimulation, we can conclude x equals to y, and that is unsound, right? So the solution, we introduce a special kind of equalities that we hope approximates the sound rewrite while being intuitive to programmers, which are called variable generic equalities. Basically, these are the equalities that doesn't peek into the semantics of the variable. So formally, it means assigning variable to this equality should hold regardless of what you assign to the variable. For example, x plus y equals to y plus x. It's variable generic, but x equals to tail of x. It's not, because the second one relies on x being a constant stream. Right? And one of the nice things about variable generic equalities is that they are closed under congruence. And that means if you start with a variable generic equality, E-matching on the variable generic equality will also generate a variable generic equality. So this means that E-matching works very well in this regard. Another challenge is unproductive cycle. This is one of the things we mentioned to like Ross and Max when we were talking, and this turns out to be a huge problem for both of us. Consider the following two rewrite rules. 2 is equal to identity function applied to 2. 3 equals to identity function applied to 3. Great, brilliant rewrite rules, very useful. And we can make this EGRAPH where like 2 is in the it's union with identity of 2, 3 is union with identity of 3, right? And we have 2 E classes, we name them 2 and 3. And if we turn them into transition systems, they look very similar. We can have a bisimulation on top of it, right? And this would unify 2 and 3, which I hope everyone here realizes is unsound. Last time I checked, 2 does not equal to 3. So it's a problem here? Intuitively, bisimulation are supposed to pick out a fixed point equation. And this is kind of the fixed point equation it picks out. It's a variable equals to the identity, defined as the identity of its variable. If you put this in Haskell, for example, you will get infinite loops when you call the variable. So this does have a unique, this does have a solution, but it's not unique. For example, 2, if you plug in here, it will also balance the equation, and 3, if you plug in here, it will also balance the equation. So really, this is the confusion between rewrite and definition. So I hope this example shows you that rewrite and definition are very different objects. And box, defined as ID of box, is not the same as box equal to ID of box. So this is very, very subtle. And the solution, from the name you probably have guessed, we have some sort of productivity tracking. So all cycles need to be guarded by a productive result. That is one of these transitions marked by : equal. If we recall our previous example, in here the cycle is going from pdef back into itself and qdef back into itself. But notice, in order to go back to itself, it needs to unfold the definition one time. And that we hope, will make it sound. And I hope I cannot find any more counterexamples. The third challenge is non-unique solution. So we have a little taste of this. Specifically, formally, why is bisimulation sound? So previously, the explanation is, well, we restrict our semantic domain to a very small subset of programs. That is, all the fixed point equation within these has to have unique solutions. And we remember that rewrites need to preserve the solutions. And finally, it basically says all the recursive definition, if you want to merge them, they have to have unique solutions. And when do things have unique solutions? For people that are familiar with ROC or AGDA, they might know like co-inductive data types. And turns out in co-inductive data, when you want to work with co-inductive data types, this is one of the things you need to make sure of, that it's all the function you define need to have a unique solution, and they have a guardedness checker to guarantee that. And the last time I checked, programmer really enjoy writing program with guardedness checker. And indeed, most of the example we've seen so far failed the uniqueness check, right? So uniqueness to us feels like a very strong restrictions, and we are trying to remove this restriction. So original solution, we were trying to do pain and suffering with techniques from iteration theory, which are theory that axiomatize the canonical solution of a fixed point equations. And after I have encountered a counterexample on Friday night, I have a new solution. Pray that Alexandra will figure everything out. OK, I think that's all I want to talk about. I hope you find this hard and depressing, and share my suffering.
Thank you so much, Cheng. We have about 6 minutes for questions. I'm happy to bring the mic to you. Phil, if you want to go ahead and start making moves to set up, that'd be great. Who's going to go first?
Hey.
So I must ask, what is the counterexample?
Oh, the counterexample is when you, that is a bit, so when you do merging, sometimes you you cut the productive cycle in half, and you only have the first half of the productive cycle, and that half can be an identity function, for example, right? And then you have unsound equalities. And that is a problem of merging variable E-class and definition E-class, because if you think of the transition coming out of it, you don't really know whether it's coming out of a variable or a definition, right? So you cannot keep track of productivity very effectively.
So maybe too obvious a question to ask, but plausibly you'd want to apply this to reason about control flow?
Yes.
So do you want to vamp a little bit on how useful this would be for reason about control flow in imperative programs?
Yes, that is a very good question. So if you know me, I did a little work called control flow GCAT a couple years ago, and it turns out to be really fast and effective, but the problem is you can only reason about control flow, right? So after every condition, it has to execute the same command. And that is very restrictive, because sometimes we want to take into account of some data flow properties, like, for example, if two commands that doesn't interact with each other, we should be able to switch them, right? This is somewhat aligned with the idea used in, for example, stream fusioning, right? And so this is one of the approach I'm trying to do, is incorporating this control flow idea with some little bit of data flow that are axiomatized as like input equations. Yeah.
Great talk. So Eli Rosenthal implemented a partition refinement algorithm in Eglog. I found it very similar. And what we learned from that TOEIC implementation is it seems there's duality between rebuilding and partition refinement, and maybe even unification. Have you thought about this?
Can you say the connection between what and partition refinement?
Rebuilding, like
Oh,
the congruence
rebuilding,
closure.
yes. So bisimulation is closed under congruence. So if you have found a bisimulation, you don't need to do rebuild under the bisimulation. But the way we do bisimulation is by checking every pair. That means like checking every pair and all the transition below it. That means that you still need to rebuild on top of it, right? So there are some efficiency to be saved if you want to save the, yeah.
Hi, Cheng.
Hi.
I wondered when you showed the example with 2 and 3 with the ID, that it would be unsounded to conclude that 2 equals 3.
Yeah.
But in Haskell, if you view those as 2 different definitions of 2 and 3, then it would be sound to conclude that they're equal.
So
Can you
that
say
is.
some-
Sorry.
Can you say something about
Yes. So that is the thing. That is the difference between definition and rewrites, right? Rewrite doesn't need to admit a canonical solution, but definition need to. In Haskell, for example, it's a least solution, right? So this is why we need iteration theory to specify what canonical solution actually satisfy. Yep.
Okay, let's thank the speaker one more time.
Sorry.